Hello, curious mind. In this video, we'll be talking about a paper that was just published on using the ionosphere to detect remote explosions. Welcome to Space Pulse. The Earth's ionosphere has long been used as a medium for remote sensing of explosive terrestrial events such as earthquakes, volcanic eruptions, and nuclear or conventional weapon detonations. However, until now, the only confirmed ionospheric detections have been of very large events that were easily detectable through other traditional global sensor systems. In a recent paper, researchers present the first clear confirmed detections of relatively low-yield 1-ton TNT equivalent chemical explosions using pulsed Doppler radar observations of isodensity layers in the ionospheric E region. These explosions were roughly 3 orders of magnitude lower yield than any previously confirmed ionospheric detection, and represent the first conclusive evidence that explosions of this size can have clear impacts on the ionosphere. This technique could improve the remote detection of both anthropogenic and natural explosive events. In this video, we will explore this breakthrough technique and its potential applications. The ionosphere is a layer of the Earth's upper atmosphere that is ionized by the sun's radiation. It has been a target for remote sensing of explosive terrestrial events. Until recently, only very large events that were easily detectable through other traditional global sensor systems, for example seismic, were confirmed ionospheric detections. However, a new technique has been developed that utilizes the ionosphere as a sensor for detecting acoustic waves generated by explosions. Explosions generate copious amounts of acoustic waves across a wide range of frequencies. While the high frequencies are quickly absorbed by the atmosphere, the lowest frequencies, in the sub-audible infrasound part of the spectrum, are capable of traveling great distances. Typically, these waves are detected on the ground using highly sensitive listening equipment, such as microbarometers. This new method utilizes the fact that the ionosphere is ionized and is therefore a good target for radar. As the sound wave passes through the ionosphere, it sloshes the bulk ions, making it show up as an oscillating radar target. This technique has been used to detect explosions with yields of 1-ton TNT equivalent, which are 500 times smaller than previous confirmed detections, using the ionosphere as a sensor for explosions. While most detections of ionospheric fluctuations caused by terrestrial events are carried out using global navigation satellite system receivers, which detect impulsive events that cause fluctuations in total electron content, or TEC. These events do not always make significant fluctuations in TEC due to the wavelengths of the infrasound generated by the explosion being significantly smaller than the integrated lengths of the ionosphere, resulting in much of the signal being integrated out. Techniques such as medium frequency, 0.3 to 3 MHz, and high frequency, 3 to 30 MHz. Doppler radar probe a single isodensity layer in the ionosphere and are not subject to signal loss through integration. These techniques have been successfully applied to detect explosive events, such as chemical explosions and rocket launches. In the study, Humming Lobo, conducted by Sandia National Laboratories at the Energetic Materials Research and Testing Center in Socorro, New Mexico, the primary scientific goal was to evaluate changes in the stratospheric infrasound propagation regime across variable seasons. The experiment consisted of 2 sets of 2 1-ton TNT equivalent chemical explosions. In each set, the 2 shots were separated by 3 minutes, and detonations were repeated at 180-second intervals and several hour intervals to examine minute and hour-scale variability in seismoacoustic signal propagation. To detect the explosions, the Air Force Research Laboratory used pulsed Doppler radar. A Digisonde portable sounder 4D was deployed at White Sands Missile Range along with 3 medium-frequency and high-frequency receive sites near Socorro. The Digisonde portable sounder 4D was run at 2 frequencies separated by 200 kHz, namely 2.4 and 2.6 MHz in O mode only. This mode allowed the researchers to monitor the vertical movements of ionospheric layers at ranges with these particular plasma frequencies. Each receiver used in this experiment was comprised of a simple cross-loop antenna connected to a 2-channel universal software radio peripheral with a basic receive daughter card, and Linux PC with a large storage device for recording data. Additionally, before each universal software radio peripheral, there was a 30 decibel low noise amplifier and a 25 to 30 decibel preamplifier at the antenna. At LWASV, 30 decibel preamplifiers were used, and the other 2 receive locations used 25 decibel units. Once range gated, the primary observable for each receive station is the phase of the signal at each frequency. which is converted to Doppler through the time derivative. As a plasma isodensity in the ionosphere is perturbed by an infrasound wave, the signature will be captured in the Doppler signal. This image shows a map and lists the coordinates of the Energetic Materials Research and Testing Center test site, Digisonde Portable Sounder 4D transmitter, medium frequency and high frequency receive sites, and their respective midpoints. There is also a 25-kilometer radius circle to show that the receive and transmitter links are all probing ionospheric points within 25 kilometers horizontal distance from the test site. The observations from the experiment match the modeled predictions, indicating the potential for future detection of explosive events. In this study, the researchers used pulsed Doppler radar to detect explosions with yields of 1 ton TNT equivalent. Each receiver measured the phase and amplitude of the 2.4 and 2.6 MHz propagation channels at 50 Hz. The Doppler signatures were visualized using a continuous wavelet transform to highlight spectral features as they evolved with time. These continuous wavelet transform plots were zoomed in to show from 4 to 10 minutes after the first shot. The researchers found that at about 0.5 Hz, 2 pulses were detected near 5.5 and 8.5 minutes at each receiver location. The properties of the pulses varied between each of the 3 stations, but the 2 shots as measured by each respective station were quite consistent. At LWASV, the peak frequency was near 0.5 Hz, with an amplitude of 7.5 meters per second. EMRTC measured a slightly higher peak frequency at 0.71 Hz and a much higher amplitude of 24 meters per second. LWANA measured a frequency of 0.7 Hz, with a peak amplitude of 7.5 meters per second. Despite some differences between each receiver measurement, the arrival times closely matched the infra-GA modeled expectations, and the 3-minute separation between pulses clearly indicates that the pulses were caused by the explosions. The continuous wavelet transforms, especially from the LWASV receiver, looked nearly identical to the infra-GA modeled expectations. The displacement, in meters, of the DPS-4D signal as measured by each of the 3 stations was also calculated, and the noise was generally higher in the LWANA and EMRTC measurements. The signal-to-noise ratio at 2.6 MHz was significantly higher than at 2.4 MHz for all 3 receiver sites, and the researchers primarily focused on 2.6 MHz. The researchers noted that the measured arrival times were slightly different for each receiver location, and there was some disagreement with the infra-GA model, which is only as good as the input atmosphere. Differences between reality and the HWM and MSI's modeled atmosphere are likely to be at fault. However, the fact that the arrival times closely match the infra-GA modeled expectations and the 3-minute separation between pulses clearly indicates that the pulses were caused by the explosions. This study shows that pulsed Doppler radar can be an effective tool for detecting explosive events. As we have seen, this study's findings have significant implications for both natural and anthropogenic explosive events. The ability to detect low-yield explosions remotely through the ionosphere using a medium and high-frequency Doppler radar is a breakthrough in the field of explosion detection. This method can be applied in various scenarios, from detecting underground nuclear tests to monitoring volcanic eruptions and earthquakes. This new technique is cost-effective and efficient, as it requires only a few simple instruments and can detect explosions from long distances. It also has potential military applications, as it can be used for early warning and situational awareness in conflict zones. Moreover, the ionospheric detection of low-yield explosions has implications for arms control and disarmament. The Comprehensive Nuclear Test Ban Treaty Organization already uses a network of seismometers to detect nuclear explosions, but this new method can provide additional evidence of non-compliance with the treaty. Overall, this study has shown that the ionosphere can be used as a remote sensing tool for detecting low-yield explosions. The results presented in this paper are a significant breakthrough in the field of explosion detection, and the new method has various applications in both civilian and military settings. The key takeaway from this study is that we have developed a new, cost-effective, and efficient technique for detecting low-yield explosions remotely through the ionosphere using a medium and high-frequency Doppler radar. I encourage you to read the full paper linked in the description for more information on this groundbreaking discovery. Leave a like if you enjoyed the video, subscribe if you want to see more like it, and share this video if your friends like learning about science. Thanks for watching.